Welcome to another lesson of sectoral structures theory. Again, I'm using this book, Sectoral Structures Theory, and we have reached chapter 6. So we still have a lot to go. Um, we want to talk about trails and a little bit of sectoral structure logic today. We've already seen what the walk of a sectoral structure is. And we've already also seen what the curve of a sectoral structure is, but we're going to do a quick refresher. So by definition, we said that a sectoral structure is a series of sectors that are connected to each other by either alpha joints when they are continuous or beta joints when they are alternating, such that the key definition such that the length of their curve adds up to 2 pi. So a circle would be a sectoral structure, a circle that's divided into equal sectors, but so do many of what we call open structures. So the curve begins at this L prime, which is a delta joint. That's what we defined it as. So it begins at the L prime, follows the curve through all the beta joints from the outside like this, passes through a beta joint, and reaches all the way to the S prime delta joint. And it adds up to a length of 2 pi. So the length of the curve of a sectoral structure must be 2 pi. And we have seen earlier that the walk of a sectoral structure also follows a similar path. It starts at the L1 and or at the L prime, ends at the S prime, and passes through every beta joint. However, from the opposite direction. So it follows the edges, just the line segments, not the curve. So it follows these edges here all the way to the S prime. And we've established that the length of the walk of a sectoral structure is always equal to 2 times lambda, where lambda is the order or the number of parts. But again, keep in mind this applies when lambda is more than 1. So when the sectoral structure is open, when it is closed, it has a walk equal to 0. Because the two delta joints are overlapping in that case. So this applies, most of what we're going to talk about today applies to open sectoral structures, meaning it excludes sectoral structures that are closed, also known as theta structures, which are basically pizzas cut into equal parts. So let's see, when is the walk of a sectoral structure equal to the curve of a sectoral structure? So W of AN equals to C of AN. We know that W is equal to 2 lambda, and we know that C is equal to 2 pi. So this would be true if and only if lambda is equal to pi. And of course, that's impossible because lambda must be a natural number, while pi is not a natural number. So, but this helps us to draw a demarcation. So we know that whenever lambda is more than or equal to 4, then the walk of the sectoral structure is greater than the curve of the sectoral structure. So if you have a sectoral structure and you want to, let's say, drive across it, and you have to decide between following the curve or the walk, look at the order of the sectoral structure. If it is 4 or greater, then the walk will take you more time. If it is, we're gonna say this. If it is, actually, even never mind. let's just keep it this way. If it is less than or equal to 3, or lambda is less than or equal to 3, then the walk will be smaller than the curve. So if the order of the sectoral structure is 1, 2, or 3, then the walk would be the easier path to follow. So both of these represent two different paths. However, they share several core properties. First, they begin at one delta joint and end at the other delta joint. Number two, they must touch every uh, beta joint. One difference is that while the curve touches every alpha joint as well, the walk does not touch any alpha joint. Now we're going to broaden this definition a little bit. Now we will talk about the trails of a sectoral structure. So trails, as a plural, uh, define any path. So any path that begins at L1 and ends at S1, or L prime and S prime, passing through every beta joint. So any path that starts at L prime, passes through a beta joint, all the beta joints, and then ends at S prime, then we call that a trail of the sectoral structure. So for example, let's go back to the same one, the 2-1-1 sectoral structure. Here we have a list of all possible trails. We begin with the most obvious one, which is the curve. So it starts here, follows the beta joints, and ends at the S1. And we're going to use a trail notation, where we will use X and O. So if we're going to follow the curve at that particular segment, we will use O. And if we're going to follow the walk at that particular segment, we will use an X. So the curve, the total curve of the sectoral structure will stay on the O. So it will be, for this one, it will be O, 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 or we will write it as O cubed. So this particular trail, which we will refer to as T1, is simply O cubed, and it has a length equal to 2 pi because it follows the curve. Now let's look at the walk. We will call this T2. The walk, we're going to stay on the x's. So this will be x, x, x. So we'll say x cubed. And the total length of this trail will be 6. That's the walk. Now let's look at ones that we're less familiar with. So let's, for example, follow this T3, which is x squared O. So this means we will do x squared, so x here, and then O at the end. So this particular trail has a length equal to, first we get the length of this arc plus, or no, sorry, we're doing x. So we get the length of this segment here, which is 1 plus 1 is 2. And then this segment here, which is 1 plus 1 is 2. So that adds up to 4. Plus the length of this arc here, which is a quarter of a circle. So that is pi over 2. So the total length of T3 will be 4 plus pi over 2. Let's look at this one, XOX. So that means 2. We walk here, that's a 2. and then an O, so we're going to stay on the outside here. That's pi over 2, and then another x, which is 2. So that also adds up to 4 plus pi over 2. So let me stop here for a second. For any two trails that have the exact same length, so in this case it's 4 plus pi over 2. If the length of two trails are identical, we will call them isometric trails. So isometric trails. Again, we're using these words a little bit loosely, but we need to identify some vocabulary to define these terms. So two isometric trails are any two trails within the same sectoral structure that have the same total length. So let's see if we can find other isometric trails. Let's look at O squared x. So this will be O plus O, that adds up to pi, plus an x here, that's 2. So, no, sorry, that doesn't add up to pi. So that adds up to pi plus pi over 4 plus 2, plus pi over 2 plus 2. So that's 3 pi over 2 plus 2. And we have OXO, which is this curve, this arc here, plus an x, so plus 2, and then another arc. So we have pi plus 2 plus pi over 2. So that also equals 2 plus 3 pi over 2. So these two also have the same length, these two trails. So we say that these are two isometric trails as well. Now, how many trails are there for a given sectoral structure, an open sectoral structure? It's pretty easy. For each part of the sectoral structure, we have two possibilities. So if a sectoral structure has an order of lambda, then the total number of trails is simply 2 to the power of lambda. Now we want to define two additional concepts. First, the boundary of a sectoral structure. So the boundary of a sectoral structure, you can see here, is basically just drawing the entire outside of the sectoral structure. So that's what we will call the boundary. And another way to think of it, it is made up of the union of the structural curve plus the walk of the sectoral structure. So really we take the sectoral structure and we're thinking of its entire perimeter. We call this the boundary, and we will say the boundary is equal to the curve plus the walk. But we already know what these quantities are equal to. We know the curve must be equal to 2 pi, and we know that the walk must be equal to 2 lambda. So therefore, the boundary must have a length of 2 pi plus 2 lambda. So here we have a new definition for a sectoral structure. We can say that it is, or an open sectoral structure, it is any sectoral sequence that has a boundary of length 2 pi plus 2 lambda. So that's how we define an open sectoral structure. Now, since the curve and the walk form the boundary, we will say that they are complementary to each other. What does that mean? That means for any two trails, if you combine them together and you end up with the um, boundary of the sectoral structure, then these two trails are complementary to one another. So the easiest one to think about is that the walk and the curve are always complementary to each other. However, other trails can also be complementary to each other. And in fact, we say that for any trail in a sectoral structure, there must be another complementary trail to it. And there must be one and only one complementary trail. So this is a very interesting way to think about it. So we will say that if T1 union T2 gives us the boundary, then these two trails are complementary to each other. Let's look at a few examples. We have the trail T3, which is x squared O. So this would be, let's try to draw it maybe. So x squared O will be something like this. And then an O. There you go. This will be complementary. We simply flip the letters. So x squared O, the complement will be O squared x. So this will be something like this. O, and then another O. No. So another O, and then an X. Notice that what we ended up with was the boundary of the sectoral structure. So therefore, we will say, in this case, we have T3. We will say that T3, the complement of T3, we will put a line over it to indicate the complement. The complement of T3 is this one, T6. And similarly, the complement of T6 is T3, and the complement of the complement gives you the initial trail. And for isometric trails, like we saw here, T3 and T4, we will use this symbol. T3 is isometric to T4. Let's continue with a few more observations. So if we want to say two trails are complementary, again, it means that the union of the two trails gives us the boundary of the sectoral structure. One thing I want to show you as well is how to find the average length of all the possible trails for a sectoral structure. So if we get all the possible trails, we add up their length and divide them by their total number. What is the length of the average trail? We'll say that this would be equal to the sum. Sorry, this is a little messy, but this is the sum of the length of all trails Tx of an, starting with x equals 1 and ending with the number of possible trails. So that will be 2 to the power of lambda divided by the total number of trails, which is again 2 to the power of lambda. So let's write this as an equation here. So we know that the total number we said is 2 to the power of lambda. And we know that every trail must have a complementary trail. So therefore, the total number of boundaries that are formed by adding all these structures together is equal to the total number of structures divided by 2, because each 2 form a single boundary. So we will say 2 to the power of lambda minus 1 times the boundary divided by 2 to the power of lambda. So this is easy to remove these. So the 2 to the lambda minus 1 is gone, and the lambda here is gone. We're left with 2. So this gives us the boundary divided by 2. We know the boundary is equal to 2 pi plus 2 lambda divided by 2. It adds up to pi plus lambda. So the average length of a trail of a sectoral structure is equal to pi plus lambda. And that way we can also divide these structural trails into two equal groups, one whose length is above average and one whose length is below average. So in this case, for example, we have three parts. So the average length will be pi plus 3. And we can divide these into two equal groups. Half of it has a length of greater than pi over 3, and half of it will be less than pi over 3. Let's do some more logic. If T1, a trail of a sectoral structure, if T1 is isometric to T2, then the complement of T1 is isometric to the complement of T2. Let's do another logic equation. If the complement of T1 is equal to T2 and T2 is isometric to T3, then T1 is isometric to the complement of T3. So let's think about it for a second. So here we said T2 and T3 are isometric. So they have the same length. And we said that the complement of T1 is equal to T2. So I can say the following. The complement of T2 is isometric to the complement of T3. And the complement of T2 is equal to T1. So therefore, T1 is isometric to the complement of T3. Thank you very much.